Hello, everybody, and welcome back to Nuclear Chemistry. Today we'll be talking about nuclear transmutations. So, you guys will be able to differentiate between two types of transmutations, which are natural and artificial, and then you'll be able to see what nuclear equations for these two processes look like, and how can you complete those equations if you're ever asked to. The nuclear transmutations is basically a process in which we have a radioisotope, and that radioisotope decays one of the six decay particles that you guys saw in table O, and then it converts into another type of element or isotope. So basically, you have your radioisotope as the reactant, and then that radioisotope converts into a decay product, which is one of the six decay particles from table O and another radioisotope or element. Now, one thing to keep in mind is that in this setup of nuclear equation, um, the mass and the charge on both sides of the equation has to be the same. So just a quick review. What is the mass? Mass is the number that you see on the top with the symbol of the element. And then your charge is the number at the bottom that you see with the symbol of the element. So charge is the same thing as the atomic number, just so you guys are not confused. So what does this mean that the mass and the charge has to be the same on both sides? This means that the mass and the charge, the sum of the mass and the charge in your reactants should be the same as the sum of the mass and the charge in your products. So basically we have two types of nuclear transmutations, which are natural and artificial. And the way both of them are different from each other is that natural transmutations are spontaneous, which means they happen on their own. They don't need any type of external force or energy, anything to get them started. So this is an example of what an equation for a natural transmutation can look like. You have a radioisotope that's converting into an other isotope and then releasing an alpha particle. Remember, helium with a mass of 4, charge of 2 is an alpha particle. And then artificial transmutations are when you have a radioisotope and it cannot be spontaneous. It cannot decay on its own. So you have to bombard that radioisotope with some sort of other decay particle, and then it can go ahead and decay something else and convert into another type of isotope. So this is the same phenomena that Rutherford did. So remember Rutherford from the Atomic Concepts chapter. He's the guy who did the gold foil experiment. So he had a gold foil and he bombarded that with alpha particles. So that was necessarily the same concept that we have for artificial transmutations. And this is what an equation for an artificial transmutation can look like. So in this specific example, you have a beryllium isotope. You are bombarding that with alpha particle, and then it's converting into a carbon isotope and releasing a neutron. So if you're ever given the equations for both natural and artificial transmutations, how can you differentiate between these two equations? Well, super simple. Just look at the number of reactants that you have. So natural transmutations are only going to have one reactant, which is your radioisotope. And then artificial transmutations are going to have two reactants. So one is your radioisotope, and the second one is the decay particle that you are bombarding that radioisotope with. So let's take a closer look at natural transmutations. So basically, as we said, they don't need any external force to get them started. And if you guys look at page 6 in your reference table packet, you have table N on page 6. This is what table N looks like. And table N has a whole bunch of radioisotopes in the first column, and then it has the names for those isotopes in the fourth column. And then in the third column, this table gives you the decay modes for all of these isotopes. Now, remember, keep in mind that these decay modes are for natural transmutation. So what this table is telling you that if you look at the first isotope there, which is gold 198, that radioisotope is always going to emit a beta negative particle naturally, okay, which means it does not need any other energy or external force to get started. So let's see how we can use this table to solve an equation or a question. So you have a question here. We are starting with a francium 220 radioisotope, and the question is asking you that what will this element transmutate into, and what will it emit in the process? So the first thing that you want to do is you want to find this isotope in this table. And there you go. We have the francium 220 right there. Now the table is telling you that this isotope is going to emit an alpha particle. And remember from table O that an alpha particle looks like this. So this is helium with a mass of 4 and a charge of 2. Okay, now we are done with this one step. Now we want to figure out that what does francium convert into after it emits a helium, after it emits an alpha particle. So to do that, now remember that concept that we just discussed a while ago, that we want to make sure the mass and the charge on both sides of the equation is equal. So to do that, you count your mass and charge on both sides that you have right now. So on the reactant side, your mass currently is 220 and your charge is 87. On the product side, your mass currently is 4 and your charge is 2. We want to make sure both of these sides have the same mass and the charge. So to figure out the mass and the charge of this unknown thing, we can just do the subtraction. So we'll do 220 minus 4, which will give us a mass of 216 for this missing product. And then for the charge, we'll do 87 minus 2, which will give us 85 as the mass of this missing product. Now remember, we also have to identify this element. Okay, we can't just leave it like mass and the charge. We have to tell what this element is. So recall from the atomic concept chapter that we use the atomic number to identify an element from the periodic table. So you go to your periodic table, you look for the element with an atomic number of 85, and it turns out to be this element right there. And boom, there you go. That's your answer. Okay. Now, sometimes for natural transmutations, you do see this type of table in Regents questions. So let's look at a type of question that you can possibly get for a table like this. So if you start from the very first isotope that's given here, let's say this is your equation, and this is telling you that if you start with the very first isotope, which is uranium, with a mass of 238 and a charge of 92. And then the equation is telling you that this isotope is converting into thallium with a mass of 234 and a charge of 90. So what the question necessarily is asking is, what is uranium emitting in this process as it's converting into thallium? So all you need to do is subtraction, because we want to make sure we have the same mass and the charge on both sides. So whatever side is bigger, in this case your reactant side is bigger, so you'll just do 238 minus 234 to get a mass of 4, and that's the mass of your missing product. And then you'll do for the charge 92 minus 90, which will give you a charge of 2 for your missing product. So now you go to table O and you see which one of those 6 decay particles has a mass of 4 and a charge of 2. And that turns out to be an alpha particle. So your answer will be an alpha particle, which is represented by helium with a mass of 4, charge of 2. Now let's look at artificial transmutation. Here's a quick example of what the equation for an artificial transmutation can look like. Remember, it has 2 products because we have a radioisotope bombarded with something, then decaying. So what this specific equation is saying right here is that you have an aluminum isotope which is being bombarded with alpha particle, and when it absorbs that alpha particle, it releases a neutron and then converts into phosphorus. Okay, so now let's say if I have rearranged the same equation and I just tell you that, well, we have aluminum 27, which is absorbing an alpha particle, and then it's emitting a neutron. But what is aluminum converting into during this process? That's your question. Now, one thing that makes artificial transmutation different from natural transmutation is that in natural, if let's say you forget to count the overall mass and charge at some point, like in the beginning, that's fine because you only have one reactant. And if you have two reactants, one of them is missing, then you only have, sorry, you have one reactant, and if you have two products, one of the products is missing, then you only have one left. So you just look at the two numbers and do the subtraction. But in case of artificial transmutation, because you have two reactants, the first step that you'll have to do is make sure that you calculate the overall mass and charge on both sides. So let's start with the reactants. To find the total mass and charge, we'll do 27 plus 4 for the mass, which will give us a mass of 31. And then we'll do 13 plus 2, which will give us a charge of 15. We'll do the same thing with the product. We only have one product right now. So the mass will be 1 and the charge will be 0. So now we can go ahead and do our subtraction, which will be step number 2, and that should give us the mass and the charge for the missing product. So we'll do 31 minus 1, so we'll have a mass of 30 for this missing product, and then 15 minus 0, we'll have a charge of 15 for this missing product. Okay, so now remember you have to identify what this element is. So you use your atomic number, go to the periodic table, find the element that has an atomic number of 15, and that turns out to be phosphorus. So there you go, boom, that is your answer. Okay? Now let's say if I rearrange the same equation again, and this time I am again telling you we have aluminum bombarded with helium converting into phosphorus, but what is this reaction emitting in the process? So you do follow the same steps. Your step number 1 will be to calculate the overall mass and charge on both sides, starting with the reactants. Your mass will be 27 plus 4, which is 31. Charge will be 13 plus 2, which is 15. Then we move on to the products. We only have one product right now, so the mass will be 30, charge will be 15. Now we can go ahead and do step number 2, which will be subtraction. So 31 minus 30 will have a charge of 1, and then 15 minus 15, 31 minus 30 will have a mass of 1, and then 15 minus 15 will have a charge of 0. Okay, so now because we are already given the elements, so we can kind of guess that this missing product should be a decay product. So we can go to table O and we can look for a decay product that has a mass of 1 and a charge of 0. And that turns out to be a neutron. And that's your answer. Now I have rearranged the same equation again. And this time I am telling you that, well, we have some radioisotope that is bombarded with alpha particle. And it's converting it to phosphorus, emitting a neutron. But what is this radioisotope that we're starting with? So this time you have to find a reactant rather than a product. So, but you follow the same steps, okay? So your step number 1 will be to calculate the overall mass and charge on both sides. So we'll start with the reactants. We only have one reactant right now, so the mass will be 4, charge will be 2. Moving on to the products. Now we'll have to do the addition. So mass will be 30 plus 1, which is 31, and then charge will be 15 plus 0, which will be 15. So now we can do the step number 2, which is subtraction. So the mass for your missing product will be 31 minus 4, which is 27, and then charge will be 15 minus 2, which is 13. So again, you'll have to identify what this element is. So you'll go to the periodic table, find the element with an atomic number of 13, because remember, charge is the same thing as the atomic number, and that will turn out to be aluminum. So there you go. That is your answer. Alrighty. So just a couple of things to take care of when you guys are working with these nuclear equations related to nuclear transmutations. The first thing that you'd want to know is whether you have a natural transmutation or an artificial transmutation. If it's natural, you can just do the subtraction. If it's artificial, you'll want to make sure that you know the total mass and charge on both sides, and then you do the subtraction. Um, Make sure that your mass and charge is equal on both sides. If you have a missing element, then you just look at the atomic number and find that element from the periodic table, which is on page 9 in your reference table packet. If you have a missing decay particle, then you look at table O and make sure you match both the mass and the charge. And table O is on page 7 in your reference table packet. When you are subtracting your numbers, just one thing to keep in mind. If let's say you have a missing product, then you will do the mass and charge of the reactant minus the mass and charge of the product. Why? Because you're missing a product. So in that case, the mass and the charge of your reactant will be greater. So you'll do greater minus less. And if it's the other way around, you have a missing reactant, then you'll do the mass and the charge of your product minus the mass and the charge of your reactant. Alrighty, so these are something to take care of when you're working with nuclear equations. So that's it for this part of this chapter, and I'll see you next time.